Today we're going to be looking at some more megaprojects, specifically Project 705 Lyra, or the Alpha-class Soviet nuclear submarine. So they spell it ALFA for some reason. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry, from engineering operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's take a look.
It's easy and fun to compare the Cold War arms race to a childish contest between NATO and the communist bloc, in which they one-upped each other in developing long and hardened metal contraptions designed to swiftly penetrate enemy defenses before spewing forth their payloads.
So to speak.
But the military-industrial complexes of both contenders were not just in it for the lulz, oh no. As a general rule of thumb, if a country's military set...
Don't know if that terminology existed back then.
Aside a sizable chunk of budget to develop a new vehicle or weapon system, it is because they need to fulfill a specific tactical, operational, or strategic goal, and or counter some potential threat. In
the way this guy talks cracks me up.
Late 1950s, the Soviet Navy had a very clear threat in mind: NATO's attack submarines, which at the time mainly outpaced their slower Soviet counterparts. Thus, the planner's goal was to develop a nuclear-powered sub that could outrun and outmaneuver all of its rivals both underwater and on the surface.
I mean, one of the key benefits of nuclear power is you don't have to refuel it very often, and you can power some pretty powerful propulsion systems.
Ultimate goal here? The interception and destruction of them. In other words, the new vessel would serve an anti-submarine warfare purpose, or ASW.
This
was the initial spark for the development of a new concept and class of Soviet vessels, the Project 705 Lyra, or Alpha class, the fastest submarines ever built.
Using the term Titanic.
It was a pretty tall order, so much so that two facilities were assigned the job: the Malachit and Volna Design Bureaus, also known as Bureau 16 and Bureau 143 respectively. The Malachit engineers were particularly suited for the task, as they had built the first ever Soviet nuclear sub, the Lenensky Komsomol. Work began in 1958 when the designers laid out the concept for their new ASW vessel. To outclass the NATO...
It's interesting how quickly nuclear submarines were an idea of what to do with nuclear power. It hadn't been around for very long in 1958.
It had to run at a speed of at least 40 knots, which is 46 miles per hour or 74 kilometers per hour. By comparison, the Skipjack class of US nuclear submarines introduced in 1959 boasted a submerged speed of 33 knots, considered unprecedented for the time. And to achieve that speed,
that's pretty good.
The designer's main concern was to reduce the sub's mass to a maximum of 1,500 tons. Weight could be reduced by employing a single reactor and by installing highly automated control functions which allow for the reduction of crew to just 9 officers and 3 warrant officers. That wasn't enough. The designer's next idea was to reconsider the hull. Instead of fitting a...
Now, I wasn't in the Navy, but a lot of my coworkers were, and on the US side, Admiral Rickover design philosophy was highly trained personnel that can intervene when these automated systems fail, and a lot of that even holds true with new nuclear reactor design today, which is a bit different because there's a lot of an emphasis on passive safety systems, which by definition do not require human intervention. But there's a bit of an old guard within the nuclear industry of people that were brought up within the nuclear navy, and the idea of, say, an emergency reactor shutdown where all the reactor operators in the control room can just sit back, kick their feet up, and just verify that all the automated systems are doing what they're supposed to do. They don't have a good feeling about it, even though it's perfectly safe. It's just a very different concept of reliance on automated systems, which, if they're safe, good, but something tells me the first of kind ones, you're going to want to test them heavily to validate that they can perform under duress.
Standard double hull made of steel, they opted for a single hull made of a titanium alloy. Not only is this metal 33% lighter than steel, but it's also stronger, which would allow the hull to withstand greater pressures without gaining weight. As such,
that's true. Titanium, I mean, it's stronger. This is designed to be a combat vessel, so that much more armor. It's also resistant to corrosion, and he mentioned lightening it so it can go faster. Though it's kind of expensive to design and fabricate into something shaped like a submarine. Not saying you can't work with it, but it needs to have pretty high standards for their fabrication, their welding techniques, and any defect in a titanium hull, well, you can lose some of that strength. And deep depth, that's going to challenge any defects, to say the very least.
The new submarine concept would run faster and deeper than its enemies. The titanium alloy would also withstand explosions better than steel, and as an added bonus, it would be non-magnetic, decreasing the chances of it being spotted via magnetic anomaly detection. Deployment work started in early 1959 as the Admiral...
So I've never operated sonar for that, but I'd imagine, any system that involves large propulsion is... one of the things you're going to hear is the reactor coolant pumps, which is why you don't always run those reactors at 100% power. It's a very different philosophy from, say, commercial nuclear power operation, when your idea is to run the nuclear reactor at full power so you're producing as much electricity as possible for your customers. Whereas here, that's not always the case. I've heard of some submarines that you would often sit at 30, and you can ramp up to 100% quickly if you need the power to maneuver in a combat situation, for instance. But they're not sitting at 100% power.
Yard in Leningrad, now St. Petersburg. Very soon, engineers realized that delivering a 1,500-ton submarine would be impossible. The Navy didn't like the idea. A single hull, not even if it was cast in titanium. As the future subs would be deployed in the near-freezing Arctic waters, military procurement insisted for a double hull, which would be more reliable. Next, the design bureaus realized that automation technology was not really up to their standards yet, and therefore many functions had to be reverted to a manual setup. 12 more than doubled to 27, requiring more space and kit for the living quarters. It became evident very soon that to achieve the desired technical reliability,
so the designation SSN is referring to fast attack submarines, in contrary to SSBM, which is the boomer submarines. And I'm not talking about persons born within a couple of decades after World War II. I'm talking about ones with nuclear missiles.
Designers had to account for a larger bulk. And then there was the question of how are they going to bring the weight down? Designers thought about reducing the shielding of the nuclear power plants, which would cause some risks as the nuclear power plant produced...
That's the first thing they think of, is reducing the number of shielding. This sounds like the Soviets.
Polonium-210, a highly radioactive isotope. Eventually, though, the design bureau realized that they could not bring the overall mass below the 2,300-ton mark, which was still good enough, but even achieving that target implied some major engineering wizardry. In this case, engineers experimented with ingenious ways to bring down the weight of the reactor and its cooling system. All the while, the construction process of...
It's not unheard of to limit the amount of shielding, but you need to do some aggressive bounding calculations to say that additional shielding was really not necessary even under accident conditions. Which, if this was done today in the US for that matter, would require some pretty hefty Nuclear Regulatory Commission reviews, which take quite a bit of time.
The first Project 705 prototype was being kept secret, as you might expect. But by 1969, the citizens of Leningrad, who took a stroll along the Neva River, could easily take a peek at the sleek, elegant, modern, and relatively small submarine. The same view could be observed from Earth's orbit, where one of the CIA satellites pointed its camera toward the Leningrad shipyards. The photos landed on the desk of Herb Lord, an experienced US naval intelligence analyst. Lord speculated that the Soviets were developing a new class of nuclear-powered submarine. Given the size of the prototype on the Neva, Lord inferred that it would likely be faster than anything the US and NATO had on offer. Moreover, the analyst noted that the Leningrad shipyard was connected by an island waterway to another facility in Severodvinsk, suggesting a large and well-financed project. Subsequent photos worried Lord even more, and they showed a hull section to be highly reflective. The analyst was puzzled, as a steel hull would normally not reflect light that much. Perhaps
giving away the titanium.
So fellow analysts laughed off that idea, as they were convinced that the Soviets did not have the capability to weld titanium. Besides, a titanium alloy would likely dissolve in seawater. Other CIA and defense intelligence...
You really think it would dissolve? I know I think they actually believe that. It's more resistant to corrosion. And titanium's pretty resistant to corrosion. It requires maintenance like anything else, but...
Agency analysts agreed with Lord, as they had been suspecting that the Soviet shipbuilding industry had been researching the use of the metal for at least a decade. Nord eventually joined forces with CIA agent Gerhard Tham, who collected a sizable number of human intelligence reports which confirmed that the Soviet Navy was indeed serious about titanium. They also learned that the new class of subs would employ small crews, a further clue that the Soviets were aiming for speed above all. Nord and Tham's analysis was confirmed in April 1969 when the Admiral Yards at Leningrad launched the first in the new class of nuclear submarines. In the Soviet Union, they were collectively known as Project 705 Lyra submarines, although they came in two variants, the 705 and the 705K. NATO militaries simply refer to them as the Alfa class.
I don't know why they don't spell it ALPHA, but that's just me. Features and bugs. Well, they're all features, right?
The Soviet shipyards assembled a total of 4 705 subs and 3 705Ks. Their characteristics were largely similar, so we'll focus on the specs of the 705s without the K. Each was 84.1 meters long, 10 meters wide, and 7.6 meters high. It was relatively light, displacing 2,300 tons on the surface and 3,180 tons when submerged. This latter weight is equivalent to approximately 30 blue whales, by the way, you're welcome. Speaking of which, if a 705 and a blue whale were to have a diving competition, the sea mammal would be victorious, as their average diving depth is 460 meters or 1,500 feet, compared to the sub's 420 meters or 1,380 feet. But those arrogant whales will be forced to eat humble krill after a speed race. While a blue whale can swim at a top speed of 17.3 knots, a 705 sub would totally outpace it, whizzing by at 41 knots. And now you might be wondering why we are
Well, the whales aren't nuclear powered.
comparing a nuclear vessel to a whale. We actually have a good reason. We'll get to it later. The record-breaking speed of each Lyra-class sub was ensured by its nuclear reactor. 705s were fitted with an OK550 model, while the 705Ks had a BM40A. In both cases, the output was the same, 155 megawatts or 40,000 horsepower. That's a nice kick up the aft section for sure, but these types of reactors need cooling, and cooling systems take up space and add to the mass of the submarine.
So they're going
and
with
the more
liquid
mass,
metal.
well, the less speed. Standard, burdensome cooling systems relied on water, but the Soviet engineers had a bit of an ingenious solution. They would use liquid metal as a coolant, more specifically a...
So what's interesting about this design is it operates in a fast neutron spectrum. So normally a nuclear power plant requires a moderator, and usually that's done by the water, but this one doesn't incorporate water into it. And what a moderator does is it slows down the neutrons so they can cause fission. This reactor, on the other hand, is designed to operate in a fast neutron spectrum, though. So it doesn't need a moderator, or not much of one. Technically, it's moderated by beryllium, but that doesn't slow down the neutrons by much. And this is quite an efficient design because it operates at a very high temperature and great thermal conductivity for heat transfer. So yeah, just a much more efficient design. The problem is the coolant still freezes at relatively high temperatures. So in this case, rather than most nuclear safety concerns are about losing coolant due to boiling, here your concern is about preventing freezing. So it has to be heated appropriately. So you can operate it at a lower pressure, but higher temperature. So there's still a lot of energy in this system. There's your trade-off. And now I get what he means about the polonium-210. That doesn't come from fission. What that does come from is the lead-bismuth alloy absorbing neutrons, becoming activated so it becomes radioactive, and it can lead to the production of radioisotopes like polonium-210. And polonium-210 is a gamma emitter. So challenges are freezing, it's corrosive, it produces activated radioisotopes that you don't normally have to worry about in other reactor designs, and it's complex. You're managing liquid metals. So there's your trade-off. But one other thing about fast reactors is you can use a wider spectrum of fuel. You can even vary your enrichment quite a bit, as it is possible for a fast neutron to fission uranium-238.
As for the human elements, the Lyra or Alpha-class subs would employ a crew of just 30 to 32, all of them officers and warrant officers. By comparison, NATO submarines were manned by about 100 personnel.
Interesting. No enlisted, though. That's, wonder how any Navy guys feel about that.
This relatively small crew had at their disposal the control room fitted with state-of-the-art equipment, such as an integrated detection system which included the Kirch sonar to spot active targets and the Zoogut sonar for mine avoidance. The helmsman would control the vessel's movements by using two joysticks standing alongside an engineer in charge of the pumps and air systems. The engineer also had sight of the sub's unmanned compartments via an advanced closed-circuit TV system. To further complement this futuristic
That's pretty advanced for back then. All of that, really.
kit, the 705s would be the first Soviet submarines to be equipped with the Accord, a computer-based control system integrating data from the sonars with the numerous weapons on board, which included VA-111 Shkval torpedoes, 81R anti-submarine missiles, MG-84 torpedo decoys, and PMT-1 mine torpedoes.
I bet they did a lot of drills on, like, misfires with weapon systems and stuff. Can't say I've ever done any of that at a civilian nuclear power plant, but you just imagine all the drills you run through usually involve something breaking, so I'm sure that's part of their training and emergency preparedness.
The Accord system would automate the identification and engagement of up to 3 simultaneous targets in rapid sequence. All in all, the Project Lyra subs definitely presented some advantages which made them stand out against their Soviet predecessors, as well as their NATO rivals. First of all, let's talk about some aspects of crew safety. As mentioned earlier, the 32 personnel on board would operate inside the central compartment of the vessel.
Now, is this 32, are these shifts of 32 people, or are they 32 people total that are manning 24/7, as in there are some of those 32 people are sleeping?
The weapons were housed in the forward section and operated by a highly automated system. The nuclear reactor, instead, was located in the aft section. Now, the crew could move anywhere during periods of rest.
Makes sense, especially an attack sub have the weapons to the front and have the thing that makes the propeller spin in the back.
During operations, the 3 sections could be sealed off from each other. This means that if the forward or aft segments were damaged in battle, the design would improve chances of crew survival. But if a 705 were to receive a critical hit, the personnel on board could easily fit into its rescue sphere, which could be detached from its main body and rise to the surface of the lifeboat. But the key selling point of the Lyra class was its speed. NATO observers, in fact, considered them the fastest submarines in the world, although that honor actually belonged to a single Soviet prototype known as K-222, which never progressed beyond that stage. The speed was achieved thanks to the innovative titanium hull and the unique design of the liquid metal-cooled nuclear reactors. But the same ingredients provided another great advantage: depth. The Lyras could withstand greater pressure than NATO submarines and thus run much deeper. The 705s could thus sit below the range of NATO weapons while launching their own torpedoes and missiles. But even if within range, the Soviet subs had another advantage: a reserve buoyancy of around 30% versus an average of 11% compared to NATO vessels. Reserve buoyancy is used as a measure of a ship's ability to sustain damage. In this case, it allowed the 705 to change direction and depth very quickly, making them a very agile target. This range of features made NATO navies very, very nervous, so much so that they rushed to develop some effective countermeasures, such as the American Mark 48 ADCAP and the British Spearfish, 2 heavy torpedoes which could reach speeds
part of the
up to
arms
80
race.
knots. The 705 submarines, however, were far from perfect naval weapons, and they were marred by several drawbacks. First of all, they were bloody noisy. Some of the noisiest subs launched by the USSR, in fact, which
makes sense as far as it being fast, so I guess they'll have to rely on their speed and maneuverability for evasion rather than being stealthy, which is a little different for submarine warfare.
Made them very easy to identify from a distance. And one may wonder, well, what's the point of a noisy submarine if they're supposed to conduct stealthy missions? Well, luckily for the crews, this defect was partially offset by the ability to dive at great depths. Another con was the cost. Titanium alloy made for a fast and durable hull, certainly, but it was almost 5 times more expensive than steel.
Not to mention the cost of your exotic liquid metal reactor. Those are not cheap. I mean, you can make them smaller and compact, but
with titanium proved to be also a massive headache for the Soviet shipyards, as welders had to work in special warehouses filled with argon gas, and they were sealed hermetically. This complex method increased the chance of mistakes, and apparently the 705's hulls were prone to cracking. But the main flaws of the Lyra/Alfa class subs were related to the nuclear reactors and their cooling system. As described in a 2002 paper by the Non-Proliferation Review, the nuclear reactors in the 705s had to be kept at temperatures above 123 degrees Celsius, lest the liquid lead bismuth coolant solidified. If it did harden, so did the nuclear fuel within the core, and if the core froze, it would have been impossible to restart the reactor.
That's one other disadvantage, is these reactor cores are single use. And, well, I don't mean reactor cores, I mean the entire reactor system is single use. Submarines can be refueled, normally, ones that use a conventional, like pressurized water reactor design. But yeah, they have to maintain that temperature, so if anything gets damaged with the heating system in combat or anything, you can lose the reactor's ability to function. Now, as far as a radiation safety is concerned, I mean, if it freezes and you got a bunch of frozen lead in there, lead is a great piece of radiation shielding, but the problem is you would essentially be relying on battery backup power, which doesn't last very long and does not keep you at your high speed, high maneuverability status. You would be just kind of drifting, running on a power level where you're barely able to survive.
The implied consequence was that if a Project Lyra submarine were left inactive for too long, the reactor would just die. To address the risk, the Soviet Navy set up a dedicated maintenance facility at Zapadnaya Lifts, submarine base overlooking the Barents Sea.
Okay.
This facility's main job was to deliver superheated steam to the reactors of the moored 705s, thus keeping the core and coolants at just the right temperature.
So interesting. So even submarines, when they're not operating on their own, they're just kind of sitting there. You have to maintain them this way. That's interesting. So yeah, even if they're inactive, they're still, dependent on some heat source, making this base even more of a target.
This method proved to be expensive and unreliable as the facility was prone to breakdowns. The only option left to the Navy was to keep the reactors running continuously, which meant that the submarines had to be kept manned at all times. Now, the problem with having...
That's true. You have a reactor that's operating, then yeah, that's true in the US as well, whether you're in the military or in the civilian fleet. Interesting though, like in civilian nuclear, if the reactor is defueled, you can actually have everyone step out of the control room and not be in violation of federal law. Now, you're not going to do that because you don't stay defueled for long, and they're usually involved in various outage maintenance activities anyway. So, ironically, that's the time when the control room is among the busiest, is when you're in the middle of an outage. But yeah, because there's no reactor, then technically you don't need to be in the control room.
Nuclear-powered reactors constantly on is that their cores generate neutrons, which interact with atoms of the bismuth-209 isotope contained in the coolant.
Okay,
the result of this interaction was bismuth-210, which then degenerates into polonium-210.
Okay.
According to the CDC, polonium-210 emits alpha particles, which carry high amounts of...
So the main hazard with alphas are an internal dose. Your skin will protect you from it mostly, but if you inadvertently ingest it, or if this becomes airborne particulate matter or something, yeah, that's a problem.
Energy that can damage or destroy genetic material and cells inside the body. Breathing or eating large quantities in a fairly short period of time can cause radiation exposure of internal organs. This can result in serious medical symptoms or death. End quote. So
that's true of any alpha source, any significant alpha source in significant quantity. Granted, it needs to be measured, but yeah, polonium-210 internal doses can be very serious.
Soviet sailors clearly were not in danger of ingesting the harmful isotope, but would likely breathe it in during lengthy missions at sea, constituting an ever-present medical hazard. The first 705 to be completed was the K-64. It launched on April 2, 1969, was commissioned on December 31, 1971, and then entrusted to Captain A.S. Pushkin. Captain Pushkin took K-64 for a spin in early 1972, or more correctly, a series of trials in the Barents Sea. During one of these test runs, the reactor experienced a breach, and the lead-bismuth coolant leaked into the outside compartment. The spill in itself provoked some damage on its own, but what was worse is that it caused the coolant to solidify permanently, backing up the reactor.
Yes.
It was a total loss.
So yeah, any individual parts of it can do it. It's not like you need the whole reactor to freeze to cause a big problem.
K-64 had to be dismantled and the reactor compartment was filled with furfural and bitumen to block radiation. The entire engine block was then shipped to the other side of the Novaya Zemlya Islands, where it was unceremoniously dumped in the Kara Sea.
So let's back up a bit. The safety and design philosophy of commercial plants versus naval reactors is a little different. Because commercial, your objective is maximizing long-term power generation and ensuring long-term public and environmental safety. That is to say, operational flexibility, fast reactor response isn't really your primary objective. It's moreover slow-moving reactor in terms of raising or lowering power and having very large design margins, which include multiple levels of reactor containment and passive safety systems that will not hesitate to shut the reactor down. Now, in naval reactors, your objective is stealth and mobility under extreme conditions, which requiring a more fast responding reactor. And shielding is more on protecting the crew rather than the external environment, which the external environment's water, which acts as a very good shield in terms of both radiation and in terms of heat. So you're not as concerned about protecting the environment at that point. And there's more of an emphasis on crash safety, because after all, it's a vehicle. So you want your reactor to move faster, and you're willing to tolerate higher operational risks because ultimately you need the reactor for your sub to move. So a passive safety system that, say, ejects the nuclear fuel out of the core into a safe and secure storage tank underneath via a temperature-activated valve. Great for commercial liquid metal reactors, not so great for naval liquid metal reactors.
Just in that year, Moscow had signed the 1972 London Convention, which prevented the disposal of radioactive debris at sea. According to the Non-Proliferation Review, the failed engine of the K-64 was eventually stored on the shores of Gremika Bay. This setback, though, it didn't deter the Soviet Navy, and 6 further subs, 3 705s and 3 705Ks, were commissioned between December 1977 and December 1981. The operational history of the Alfa-class submarines was largely unremarkable, as they never saw combat. We may argue that their mere existence, however, worried NATO enough for the US and the UK to develop new and faster types of torpedoes.
Just like any other significant advancement within the Cold War, it panics the other side.
As mentioned earlier, vessels K-373 and K-316 experienced no issues during their time in service. They were eventually decommissioned in 1990 and dismantled in 1994. K-493 survived the fall of the...
Which would be after their life cycle, because those reactors aren't designed to be refueled.
Soviet Union, serving with the Russian Navy until 1995, when it was refitted with a water-cooled VM4 reactor. After the brief...
Or you replace the reactor. Yeah, you have to replace the whole thing in this case. And in there, they opted for a different design.
Servicing hiatus, it re-entered duty as a training vessel before its eventual decommissioning in 1996 and dismantling in 1997. The remaining 3 Lyra submarines had a somewhat more troubled history. K-123 was launched on December 26, 1977, and then experienced a major accident in 1982, when a lead bismuth spill contaminated the entire reactor compartment. It took the Navy almost 9 years to replace the compartment, but the sub took to the seas again in 1991, now numbered B-123. It ceased its operations in 1993 and then was decommissioned in 1995. According to the Non-Proliferation Review again, also K-463 experienced a reactor accident, although no details are available. The damage was...
Yeah, not surprised. You see, a lot of this stuff is redacted. You see, I didn't know about that one because it's military classified, and knowing how the Soviets tried to cover up every nuclear accident they had, like Chernobyl, for instance, they just couldn't because it set off high radiation alarms in Scandinavia.
Reparable, and K-463 was decommissioned in 1986. So that leaves us with the 6th vessel, K-432. No reactor faults for this one, but a fate far more unpredictable. Quoting again from the Non-Proliferation Review. In a freak accident, the submarine hit a whale during its sea trials, necessitating major repairs that were completed in 1988. However, the submarine was never recommissioned. By 1996, all 7 Project 705 Lyra or Alfa-class submarines had been decommissioned and were all undergoing their dismantling. The physical breakdown of a titanium-hulled, nuclear-powered submarine is a complex and delicate affair, and the Russian Navy and its contractors had to follow a meticulous process.
There's a whole art and science of decommissioning anything nuclear. So yeah, especially a titanium submarine that surrounds said nuclear reactor. Yeah, I'm willing to bet there's a lot to it.
First, subs had to be relocated to a specialized facility, the Sevmar shipyard in Severodvinsk. There, all weapons, explosives, and sensitive equipment were removed by the Navy and reassigned to other units. Next, contractors stripped the vessel of loose furnishings, spare parts, tools, and other expendable material. Once a sub was dry docked, specialized personnel would open the hull about the reactor and move on to the most dangerous phase, removing the radioactive fuel from the core. This hazardous cargo would be temporarily stored at the shipyard before being transported to an external facility for it to be reprocessed. As per the titanium hull, it would be recycled and sold as scrap metal. In the Navy's calculations, the revenue from such sales should have covered the overall cost of the dismantling process. In reality, the advanced equipment required to defuel the reactors and strip the titanium.
Yeah, any kind of decommissioning, even for a relatively small naval reactor, there's a lot to it. So he mentioned defueling, you shut down and remove the reactor core, you have to drain and clean every system that the radioactive material interacted with. Now, the reactor compartment would probably be taken out as a single sealed unit just in order to minimize radiation exposure during the dismantling process, and they would need to be dismantled and stored possibly in separate facilities from the other contaminated materials, because it just depends on the nature of the contamination and how you would need to sort and classify them. And even the site that does the dismantling would probably have to undergo some level of environmental remediation and cleaning, essentially, because you're going to contaminate some of the tools that were utilized. You could even see some of the challenges with a tightly packed reactor and shielding that could just make it physically more complex in order to dismantle and sort out. I'm actually kind of surprised they broke even with the salvage cost of the titanium for decommissioning one of those reactors, if they even really did.
Hull largely offset those proceeds, meaning that the Sevmar shipyards lost about $2.5 million per submarine in the late 1990s, almost $5 million each in 2024.
Yeah,
value.
That's not surprising.
The Project 705 Lyra-class submarines were definitely a source of concern for NATO navies. Even at the developmental stage, they kept DIA and CIA analysts busy collecting human and satellite intelligence. And once launched, they proved to the West that the Soviet Union had the right skills and resources to pull off what was believed almost impossible, i.e. developing small, highly automated titanium-hulled vessels which could be run by a nimble crew. That fact in itself spurred the US and the UK to develop suitable weapons that could counter the 705s. In terms of practical results, however, the boat had little to brag about. 4 out of the 7 vessels experienced serious accidents, which put them out of commission almost immediately. Moreover, even those subs which functioned.
The 705Ks had a more reliable reactor design that was less susceptible to that whole freezing thing, but either way, I mean, it's experimental, new technology, scary, but yeah, ultimately wonder if it was worth it.
As intended, were marred by complex and costly maintenance processes, which hardly justified the enormous investment. The effort poured into the 705s by the Soviet Navy was not to be entirely lost, though. If considered as an intermediate phase or a stepping stone, Project Lyra enabled Soviet shipyards to perfect welding practices, propulsion systems, and automated control equipment, which trickled down into future designs, such as the Akula class. As long as the Cold War was on, NATO navies would still be wary of the Red Menace from the deep.
Sounds like some sort of evil shark. That was an interesting one. Thanks so much for the recommendation, and thanks so much for watching. I'll see you next time.